Okay, quantum mechanics. Now, all that we're going to do here is lay the foundations that's necessary to understand electron configurations, which will be our next topic. In the 1920s and 30s, the Bohr model underwent many revisions and eventually became what we now call quantum mechanics. A little video clip on this.
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom, which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
And that's what we refer to it as, an electron cloud. I'm going to kind of clarify the term quantum. Quantum refers to the fact that electrons can have only a certain amount of energy. It's like Bohr's energy levels. Remember that the electron could be at one energy level or another energy level, but it couldn't be anywhere in between. So this idea that energy is quantized, that could have only certain amounts, is where the term quantum mechanics comes from. This is the 1927 Solvay conference in Brussels, and here we have very renowned physicists from around the world that gathered together to discuss quantum mechanics. In the 1920s and 30s, quantum mechanics was an emerging theory, and there was tremendous excitement because it answered so many questions. Many of these physicists you may have heard of or you will hear of someday. Here's Albert Einstein, Niels Bohr, de Broglie, remember electron waves from last time, Werner Heisenberg, that we'll talk about in a few minutes, Marie Curie, Max Planck, and many others. Names are down here. Quantum mechanics, a mathematical model of the atom. Now, when we say that, we're not talking about algebra or trigonometry. It's pretty high-level math. This is called the Schrodinger equation, just to give you kind of a taste of what quantum mechanical equations look like. And I'll put a link in today's lesson file where you can take a look at a Wikipedia page that shows many of the quantum mechanical equations to kind of give you a taste of what that type of math looks like. I'm sure many of you like math, and you might be intrigued by taking a look. Developed throughout the 1920s by many different physicists, many of whom you just saw. Explains the chemical properties of the elements. Now, this was huge. Before quantum mechanics, we had no idea why elements behaved the way they do chemically. Now, we had certainly come a long way in understanding the structure of an atom, the nucleus, and just that atoms exist at all. But as far as the chemical properties of the elements, nobody had any idea. Quantum mechanics explains it beautifully. Predicts that Bohr's energy level contains sublevels, analogous to an upstairs and downstairs. So you can think of the energy levels as being a floor of an apartment building. Well, quantum mechanics says it's not quite that cut and dry. Those energy levels really have kind of an upstairs and downstairs, and we call those sublevels. Predicts that within sublevels are orbitals that represent the most probable location for finding an electron. You can kind of think of it as a room. So we have the energy levels, which like the floor of an apartment building, and then sublevels and upstairs and downstairs. And then in those upstairs and downstairs, you have these rooms. And inside those rooms are where electrons are located. And of course, the term orbital is a play on the word orbit. One of the most successful and useful theories we have. It laid the foundation for our modern technological world. Nothing that you associate with modern technology would exist were it not for quantum mechanics. There would be no cell phones, the computers that we use, modern medicine, nothing that we associate with our modern world would exist were it not for quantum mechanics. One of the more troubling aspects of quantum mechanics, and there were many, was what's called the Heisenberg uncertainty principle, devised by Werner Heisenberg, 1901-1976, a Nobel laureate. And the Heisenberg uncertainty principle states that it is not possible to know both the position and path of an electron. Heisenberg's big insight was recognizing that we were never going to be able to look inside an atom and literally see what's going on. The electrons are just too small. The very act of observing an electron will change what it's doing. How do you see something from a distance? Well, you shine a light on it and the light bounces back and you see it. Well, in order to see an electron, we would have to shine something on it, some sort of radiation, and have it bounce back. But the electrons are just too small. If we were to shine something on it, it would knock it all over the place. So the uncertainty principle is that the very act of observing something changes it, so we'll never be certain what's going on. The position of an electron can only be approximated using mathematical modeling called probability theory, like rolling dice. This really troubled a lot of physicists, in particular Einstein. Quantum mechanics just drove him nuts. Orbitals, regions of space occupied by electrons. And so here we have, remember, each one of these little tick marks is not an electron, but a probability of finding an electron, the nucleus there in the center. The dots represent possible locations of an electron. The shape is defined by a 90% probability of finding an electron. So if we were to look at all of those little tick marks and draw a boundary around 90% of them, we would end up, in this case, with a circle. As we'll see in a second, there are different shapes of these orbitals, and this is a s orbital, spherical in shape. So the shape is defined by a 90% probability of finding the electron. Now, the little animation that you're looking at here is really a bit too clean. The tick marks would, it's very dense in the center here, and it gets less dense, and it would continue on. But this would be 90% boundary. There are 4 types of orbitals, S, P, D, and F. The letters come from descriptors of spectral lines. When you look at an emission spectra of an element, the emission lines, they're not sharp, or they're not straight, rigid lines. They kind of have different aspects to them. And the S, P, D, and F are from the descriptors of those spectral lines. S is for sharp, P is for principal, D is for diffuse, and F is for fundamental. You don't need to know that, but it's kind of interesting. And I always hated it when I would be taught something and all of a sudden something like that would be presented without explanation. So why S, P, D, and F? Well, they come from the descriptors of spectral lines. So S orbitals, now S orbitals are in fact spherical, and often people will say, well, the S stands for spherical, but that falls apart with the P, D, and F. But anyways, but it's useful, you can remember that. So the S orbitals have this spherical shape. The P orbitals often are referred to as dumbbell shaped, and you can see that they're perpendicular to one another along the X, Y, and Z axes. And there's 3 of them. Now they've been pulled apart so that you can better see them, but in reality they would be superimposed upon one another. So the axis here, the origin, is the nucleus of the atom, of course, and so we have the same nucleus for each of these. They just need to be pulled together. There are 3 orbitals in a p sublevel. And this is the most important thing to remember. The S sublevel has 1 orbital. The P sublevel has 3 orbitals. The D sublevel has 5 orbitals. And we'll look at the F in a second, but let me explain a little bit how these shapes came into being. When we look at the spectral lines of an element, the electrons are moving to and from a particular energy level. Well, we can easily measure the amount of energy that an electron would have when it does that. So what we do is we take that energy, that amount of energy, and we plug it into the mathematical model of quantum mechanics, those equations that some of you may look at when I share that link. They plug those in, and little by little, it plots out. Back in the day, now we do it much faster. It will plot out the shape of these orbitals. And so the electrons that belong, say, to this orbital, 90% of the time, they're in these regions that are here shaded blue. So it's just kind of crazy shapes. But were it not for these shapes, our understanding of the elements would not be what it is. It's one of the foundational aspects of quantum mechanics is the shape of orbitals. Were it not for these shapes of orbitals, we would not understand the elements. So they're not just a kind of an amusement. They're fundamental in understanding the chemical properties of the elements. I'm repeating myself, I'm sorry. Okay, and then the F sublevel has 7 orbitals. Even crazier. Now, each one of these orbitals, an electron, a maximum of 2 electrons can occupy that space altogether. Like if this was a filled orbital, 2 electrons, that's the maximum number of electrons that could fill that. The same thing for this and all orbitals. 2 is the maximum number. Now you do need to know the shape of the S and P orbitals. S is spherical, the P like 3 dumbbells, often referred to as dumbbells, perpendicular to one another along the X, Y, and Z axes. Okay, now let's look at Bohr's model. Remember the energy levels from Bohr's model, but let's take it into quantum mechanics. And Niels Bohr, by the way, was one of the leaders of quantum mechanics. So his model, the Bohr model of the hydrogen atom, was the starting point for quantum mechanics. He was as involved in the development of quantum mechanics as anyone. So taking his energy levels one by one, we're going to break it apart and look at it in terms of being a quantum mechanical model. So the first energy level has one sublevel called the S. And the S sublevel has one orbital, and we're letting boxes represent the orbitals here instead of those crazy shapes. The second energy level has 2 sublevels, the S and the P. The third energy level has 3 sublevels, the S, the P, and the D. Now notice that the number of orbitals in a sublevel doesn't change for the S, P, and you'll see for the D as well. So the S's are always just 1 orbital, the P is always 3 orbitals, D's are always 5, F's are always 7. The fourth energy level has 4 sublevels, the S, the P, the D, and the F. Now, going back to the apartment floor analogy, so let's look at the 4th energy level. So you can think of that as being the 4th floor of an apartment building that has an upstairs and downstairs, and on each of those levels, sublevels, you have a different number of rooms or orbitals. It's a very simplistic way of looking at it, but it works. Okay, let's summarize what we know about the energy levels and how electrons occupy those energy levels. So the principal energy level, 1, 2, 3, 4, 5, 6, remember, goes off into infinity. We're just going to 6 here. The number of sublevels that we have will turn out to be exactly the same number. And the number of orbitals that you would have in a sublevel are always going to be the same, as you'll see. So the first energy level has 1 sublevel, and in that sublevel is the S, and we have 1 orbital in the S. The P, D, and F don't exist yet. The second energy level has an S and a P, 1 S and 3 P orbitals. The third energy level has an S, a P, and a D, 1, 3, 5 orbitals. The fourth energy level has 1 S, 3 Ps, 5 Ds, and 7 Fs. Now, remember that The sublevel is the SPDNF. What we're counting here are the number of orbitals, like rooms, in those sublevels. Now the fifth energy level, 1, 3, 5, 7, just like the fourth, and you might say, well, what about, shouldn't we have another column here? Well, it turns out we don't need to go any further than this to understand all of the elements on the periodic table, which will make more sense to you when we get to the periodic table, but you might remember the inner transition elements that are pulled, those two rows that are pulled below the periodic table, those belong to the 4 and 5F, and they are the end of the periodic table, or close to it, and we don't need to go any further than that. And then the 6 would be the same. Again, we could continue on. You kind of think about the sublevels that we're not writing here being empty floors above in that apartment building. And what they do, if they ever need to mathematically think about it, it's kind of funny, really. Remember that the SPD and F the letters come from the descriptors of spectral lines. Well, what they do is after F, they figure, well, we're already kind of well into the alphabet, so let's just continue G, H, I, J, K. But again, we don't need to worry about that. Now, the number of sublevels that we have is exactly equal to the principal energy level. So like the fourth principal energy level has 4 sublevels. What are those 4 sublevels? Is the SPDF. Okay, how about the total number of orbitals? Well, all we need to do is add together the number that we have here. So in the first energy level, we have 1 orbital. In the second, 1 plus 3, 4. The third, 1 plus 3 plus 5, 9, etc. Okay. Now, of course, we don't have the columns here. It's not going to just be 16 as we go up, but we can kind of deduce what's going on here. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So 5 squared must be 25. 6 squared must be 36. So the total number of orbitals is just n squared, whatever n is. So 25, 36. Now we haven't gotten there yet, but we will next time. One of the rules for electron configuration is called the Pauli exclusion, the Pauli exclusion principle, which states that you can have a maximum of 2 electrons in any orbital. So all we need to do here to determine the maximum number of electrons that we could have in a given energy level is double the number of orbitals, because we can have maximum of 2 electrons in any one. So it would be 2n squared. So 2, 8, 18, 32, 50, 72. Okay, so it's a nice summary of the arrangement of sublevels, orbitals, and total number of orbitals and total number of electrons for each of the principal energy levels. It's a handy relationship to have. If you're finding all of this rather confusing, you are in good company. Niels Bohr said, if anybody says he can think about quantum physics without getting giddy, it's kind of like dizzy, crazy, that only shows he has not understood the first thing about them. And Einstein. Quantum mechanics is certainly imposing, but an inner voice tells me that it is not the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. Einstein used to kind of play around with this concept of God that people have. He was not religious at all, but he felt that it was an easy way to explain to people the laws of nature. So rather than saying this is not the way that nature works, he would say that this is not the way God works. I, at any rate, am convinced that he does not throw dice. It means that the location of electron is not going to be governed by some sort of weird probability theory. There has to be exact laws to explain it. And actually, he went to his dying day in 1955 trying to revise quantum mechanics. But unfortunately, by that time, quantum mechanics was so wildly accepted that it was really a losing battle. And then Richard Feynman. I think I can say I can safely say that nobody understands quantum mechanics. If ever you get a chance, talk to Ms. Wall about Richard Feynman. She's a huge fan of his, and rightfully so. He's an amazing man. Okay. Remember that I will put some links on today's lesson file that I think many of you will find interesting. But for now, that is the end of our notes.